Dear students, in this lecture, I'm trying to explain the start effect on the first excited state of hydrogen atom. In 1913, the Stark find an effect phenomena that when an atom is placed in a uniform electric field, the energy levels of the atom is shifted by some amount. Due to the shifting of this energy level, there is a spectral line or the splitting of a spectral line. This effect is known as Stark effect, and the last class we already discussed the ground state energy of Stark effect. The first order correction, ground state energy of the Stark effect don't show the first order Stark correction. There is not showing the ground state energy of the hydrogen atom, don't show the first order correction. But it shows the quadratic effect, it shows the quadratic, it means the second order correction, there is some significant amount is there. But here what I am trying to explain is, in first excited state of hydrogen atom, the first excited state of hydrogen atom, there is some important point is here. The first excited state of hydrogen atom is a four-fold degenerated. So we cannot apply the non-degenerate perturbation, time-independent perturbation theory for this case. Why? The first excited state of hydrogen atom is a four-fold degenerated. So for the degenerate case, we already studied the degenerate theory for time-independent perturbation theory. So in this formulation, I try to explain in that manner degenerate case of a time-independent perturbation theory. So what is the perturbation here? The perturbation for this system, that the system is hydrogen atom, is the electric field. So I will explain. If suppose an atom is acting as a dipole, so due to the electric field, suppose E is the electric field, R is the position of electron in the atom, and mu is the dipole moment of this electron. If mu is the dipole moment, it can denote as E into R. Is interacting with this much dipole is interacting with the applied electric field. So H prime is nothing but is a perturbation is equal to minus mu dot E. So E mu A dot B form. So it is mu is equal to minus E R. So minus E minus will cancel E R E cos theta. R cos theta is Z term because we are applying the electric field along Z axis. So E is Z. So this is the perturbation. So this is the perturbed quantity. So our first excited state of hydrogen atom we can denote as the states of hydrogen atom. So in spherical coordinates we can express in terms of n, principal quantum number, orbital angular number, and magnetic quantum number, n, m or ml. So in that manner, the first excited state means n is equal to 2. It has the four possible state 200, 210, 211, 21 minus 1. Energy depend only on the n. So that's why the all four states having same energy. That's why it's called four-fold degenerated. So here we need to use the degenerate perturbation theory. Time independent degenerate case. So I need to, what is the form of H prime? I need to find it. In the general formulation, I consider two-fold degenerated. In that we know HNN, HLL and HNL, HLL, 2 by 2 matrix we are now. In that way, we have H prime is a four-fold degenerated. We want to create what is the form of H prime. So H prime is nothing but a 16 element matrix. I will give a shortcut to produce what is the matrix form. So the states the ket notation of the states I denote as a row, and the bra notation of the states I denote as a column. And I can multiply each term here. This term is bra 200 H prime 200, and this term is bra 200 H prime 210, 200 H prime 211, and so on. And finally this 4 by 4 16 element 4 by 4 matrix is known as H prime. So I done here is that same matrix, and the matrix we know the formulation, the determinant we need to find, and the eigenvalue of the determinants will give the correction terms. So this is the determinant. I can find here first order correction. I can find here first order correction. So we know if a determinant is a minus lambda I form. So lambda is eigenvalue. In that case, in the here we need to find e of 1. So in eigenvalue this one and this one and the diagonal term we can, and we need to find the solution, and this is the we need to find it's equal to 0. We have to equate a minus lambda determinant equal to 0. In the same way, the determinant of this matrix we can find the 0 and e of 1 and that way. So the important thing is we need to find the integration of all these terms. What is the integration of this one? What is the integration of this? And we need to find a 60 terms integration. But we are not going to do all this one. Here the some conditions are here only 2 terms survives integration. Out of the 16, only 2 terms are non-zero terms. All others are 0. So we can all elements differ ml values. So here 0 0 ml are the same. Here 0 0 ml's are same. But here 1 and here 0. Here 0, here 0 same. Minus 1 0. So those who are all ml values are different. It's vanished because the orthogonality of NLM stays. Because orthonormality condition here h prime is nothing but e is n. So we can multiply. So orthonormality condition will give differ ml values all are give 0. You can do it there. And the 4 diagonal elements. All diagonal elements are 0 because they are same parity. Because 2 0 0 2 0 0 they are even parity. But h prime, yeah, h prime is what? It's an odd factor z or r e cos theta. This only is z is an odd thing. So odd and even. In that way, same parity, but h prime is an odd parity. In that way, we can explain that will give the 0. Otherwise, we can find it. It's no problem. And the remaining 2 terms, what are the 2 terms here I am going to explain. One is 2 1 0 and h prime 2 0 0, and this one 2 0 0 h prime and 2 1 1. Sorry, h prime 2 0 0 and h prime 2 1 0 h prime 2 0 0 and 2 0 0 h prime 2 1 0. Is it I made a mistake here somewhere. This is 2 0 0 h prime 2 0 0 here, but this one 2 0 0 2 1 0 here. This is 2 1 1. Sorry. It's not a problem, but these 2 terms only the non-vanishing term. It will give non-zero value. We need to find that integration. But there is an important point is both are same. The values are same. You can find the integration, and all other 14 terms will give 0. So we not bother about it. It will be equal to 0. And first of all, next step is to find what is the integration of these 2. So we can do it. Okay, so we need to find these values first. So I already explained there is out of 16 terms 2 is non-zero. So these are the 2 terms 2 1 0 plus 2 1 0 x prime 2 0 0. But there is a key thing is that both are same value. We get same value. So we need to find this integration. So what is the ground state energy with the 2 0 0? Sorry, the wave function for 2 0 0 is 1 by 4 root 2 pi 1 by a 0 raised to 3 by 2 2 minus r by a 0 exponential minus r by 2 a 0. What is state for 2 1 0? Is equal to 1 by 4 root 2 pi 1 by a 0 raised to 3 by 2 r by a 0 exponential minus r by 2 a 0 cos theta. So I need to find first one 2 0 0 x prime. So this 2 0 0 x prime So the usual integration is, actually this is what? Integration psi star, sorry, sine 200 tan h prime sine 210 d tau. Actually both are same. So what is d tau here? D tau is nothing but r square dr sin theta d theta d phi. This is d tau. So you already know these things. So I just written all these steps. So I took this integration this one in the psi star form, and both are the sum terms are 1 by 4 and 1 by 4 16 root 22 2 into 16 32. So 1 by 32 by a0 3 by 2 0 a0 3 by 2 0, it's become a0 cube. Here 1 a0 is 1, so a0 is to 4. So here in h prime, the h prime is here. In h prime, what was h prime? Is equal to e r cos theta. So this will come here, by 32 by a0 is a constant. Then one integration for d phi, one integration for theta, one integration for r. So 0 to 2 pi integration for d phi, and 0 to pi integration for d theta, 0 to infinity, and the terms are the here 2 minus r by a0. Here 1 r is there in our r square dr, 1 r is there. Here 1 r is there, in h prime 1 r is there, and here is 1 other. This r square will come here, and exponential minus r by 2a0 into exponential minus r by 2a0. 1 of into r is written plus 1, so exponential minus r by a0 into r square. So this is integration form, and this integration is this cos theta will come here, and one cos theta come from the, so what is this cos theta, and both are become cos square theta. Then the d tau, r square sin theta dr d theta d phi, r square sin theta dr d theta d phi. And when you take the splitting the integration, so this 32 pi is 0 to 2 pi d phi integration, 0 to 2 pi d phi integration means d phi integration means phi, and 0 to 2 pi means 2 pi. So when taking this integration, we get a 2 pi. The 2 pi will cancel, 32 2 will get 16. So by 16 is 0 raised to 4. Then remaining integration 0 to pi, here cos square sin theta d theta, cos square sin theta d theta, and r integration 0 to infinity. This r square is there, here r square is there, so r raised to 4 will become 2 into r raised to 4 minus r raised to 5 by a0. I took the all r terms are inside the bracket, and exponential minus r by 0 into dr. So we need to find this integration and this integration. And here one thing is here, in standard integral 0 to infinity x raised to n e power minus ax dx. So this is in this form, so we can use this standard integral 0 to infinity x raised to n 0 a exponential minus dx will give n factorial by a raised to n plus 1. Here this is a x coefficient. In this case x coefficient is 1 by a0. So in that form a raised to n plus 1. You can find it. And here is one integration 0 to pi cos square theta sin theta d theta. Here is very easily we can integrate it in one method. So I give the cos theta as a x. Then this differentiation minus sin theta d theta I can take dx. So this integration become x square dx. So limit 0 to pi. So theta equal to 0, x become, here theta is equal to 0 means cos 0 is equal to 1. So x is equal to 1. And theta is equal to pi means x is equal to minus 1. So integration limit is, instead of 0 to pi, I can use minus 1 to 1. So 1 to minus 1, here minus is there, it will minus 1 to 1. And take the integration, s square integration s cube by 3. I will apply the limit, it becomes 2 by 3. So this one is 2 by 3. And while taking this one, you can easily do here 2 terms are 2r raised to 4 exponential minus r. So n here in this term x raised to n, this is 4, so 4 factorial by a raised to, a is 1 by a0, 1 by a0 to our denominator a0 n plus 1, 4 plus 1 is equal to 5. Here only 2 is the 2. Okay, and minus r raised to 5, so 5 factorial by a0 is already here, and a raised to n plus 1, this will be a raised to 6. So this becomes 5, this will cancel, and we can cancel this all term. This is it's equal to 2 into 4 factorial, and 4 factorial is 1 into 2 into 3 into 4. This becomes 148, and this becomes 5 factorial is around 120. So this is equal to minus 72 a0 5. So you can find this. So this term becomes 72 minus 72 a0. So you can do this also, and just cancel some term here. 72 and 16, 2 by 3. By cancelling, this will end up with minus 3. So this is our value of this integration. We already told both are same, so you can do this integration also. You will end up with the same equation. The same step is not at all changing. Both are same. So this. Now we already told all other 40 terms are 0. So we can create the h prime here. H prime is all terms are 0 except these two terms. So that's minus 3a0 and minus 3a0. And what is the next thing is the determinant we need to find. So what is the determinant of this matrix? We need this is eigenvalue e2 prime. So this minus e2 prime, this minus e2 prime we are given. So this is our 0. So 0 minus this means minus, and these are the. So we can find the solution of this determinant. We will get a 4 solution. So in lambda e2 raised to 1 raised to 4 term, and out of these 4 roots we will get a 4 roots. The 4 roots is one root is 3ea0 and another root is minus 3ea0, and the third and fourth are 2 zeros we can get in. So it means what? There is a 2 different roots, and the third and fourth are 0. So the state here we can conclude that the state 2 0 0 and 2 1 0 are affected by electric field. So 2 states are affected by electric field. That's why we are getting 2 different eigenvalues here. Eigenvalue is a solution for here roots. And 2 1 1 and 2 1 minus 1 are not affected by electric field. So 4 degenerated. Out of 4 degenerated, the 2 are shifted with some value, and the other 2s are remaining unaffected. So the state 2 0 0 and 2 1 0 are shifted with some value, but 2 1 1 and 2 1 minus are not at all affected due to this electric field. So the 4 degeneracy lifted partially. There is initially the 4 degeneracy was there, but now the 4 degeneracy shift. 2 are remove the degeneracy, and other 2 remain same. So this is very important point. Now what we are going to find, these are the roots. So the eigenvalue we got. So by we already know in degenerate time independent perturbation theory we getting 2 equations like this for 2-fold degenerate case. Now the case is like something like a same thing, and we can use this equation or this equation by giving the eigenvalue instead of this e and 1, this eigenvalue we can apply for first case 2 0 0. That is, we need to apply this 3a0, and we can find the value of Cn and Cn, and by using the normalization condition also we can find the region, and by substituting this eigenvalue we can find an eigenfunction, and by substituting this eigenvalue we can find an eigenfunction. So then we need to check what are the eigenfunction for this one. You can write it, this one. We need to find the eigenfunction corresponding to this. So here I will try to find the eigenstate corresponding to each eigenvalue. We have 4 rows, so in which I substitute I can take any one of this equation. I cancel this equation. H prime nn minus En 0 Cn plus H prime nn Cn is equal to 0. For the eigenvalue 3 Es 0, I took first consider this one. I substitute this one here, so that this state is corresponding to 2 0 0 states. And for this states, suppose H prime nn with these states will give 0. We already in that determinant we already told 2 0 state with H prime will give 0, and H prime nl will give the same value minus 3 E 0. So here minus 3 E 0, here minus 3 E 0 into Cn, minus 3 E 0 into Cn. From this one we can find Cn by Cl is equal to minus 1. Here we get a then here by substituting here we will Cn by Cl is equal to minus 1. And one more thing, there is a normalization condition for this coefficient, that is Cn square plus Cl square is equal to 1. From this to expression this condition, we will end up with Cn having a 1 by root 2. Cl is possibilities minus 1 by root 2. So if you have Cn and Cl, the corresponding eigenstate we can pronounce 1 by root 2. The state is 2 0 0 minus 1 by root 2 2 1 0. So this is eigenstate corresponding with an eigenvalue 3 E 0. And the same way, here by considering the second eigenvalue minus 3 E 0, we will end up with the other eigenstate with 1 by root 2 2 0 0 plus 2 1 0. So these are the two eigenstates corresponding to the two eigenvalue 3 E 0 and minus 3 E 0. So what is the final conclusion here? Initially the fourfold degenerate, the fourth state having the same energy E2 0. Now due to this electric field, the states are shifted with some value. The one energy is shifted with E2 0 plus 3 A 0, and another energy is shifted with E2 0 minus 3 A 0, and two states are unaffected, and both two states having the same energy E2 0. E2 0 means the unperturbed energy. The E2 0 plus 3 A 0, the corresponding state is 1 by root 2 2 0 0 minus 2 1 0. 2 0 minus 3 A 0 energy. Its eigenstate is 1 by root 2 2 0 0 plus 2 1 0. What is the conclusion from this on this point is the hydrogen atom in the first excited state we know possess the permanent dipole moment having the value 3 E 0. So this much 3 E having the eigenvalue. So the dipole moment, this dipole moment having three orientation. One state is parallel to the external electric field. Other state is suppose one state is parallel to the electric field, and another state is anti-parallel to the electric field, and other two states which are the 2 1 1 and 2 1 minus and do not possess the dipole moment, which are the zero component along the field. It's the field two states 2 1 1 and 2 1 minus 1 having the zero component along this field, and its having the its conclusion is do not possess the do not possess the states 2 1 1 and 2 1 minus 1 do not have the first order interaction to with the field. So this is all about the Stark effect. What we already tried to explain here, the first excited state of hydrogen atom is showing the Stark effect. It means the first in the last lecture we have discussed that the ground state energy of hydrogen atom do not show the Stark effect, and it's the second order correction. It's the quadratic correction is the quadratic effect is showing, but the first order correction to the ground state energy is not showing the Stark effect. But here the first excited state is showing the Stark effect for the. It's also it's the fourfold degenerated state, and the perturbation process the removal of degeneracy partial. It's not completely removed because the two states are in the same energy. So this is all about the Stark effect, and let's go through this all and read the textbook. You may get the good idea. So thank you.